past 3 months, I've been doing a course on Coursera on machine learning, and I've seen the future. It's amazing, and that's kind of whetted my appetite to have a look into learning technologies in general. I'm going through a courseware book from a lot of universities use this on AI. It's about 1,200 pages. It's a massive subject, but I'm extremely excited about it. So just wanted to give you, something to whet your appetite, to run you through a hello world from the machine learning world by looking at a topic called linear regression. And this is a topic that introduces some of the concepts that is used a lot in machine learning. And where I'm driving is that I think we should be building our own machine learning capability, and I'm looking for volunteers to come and help out. So I just want to have a look at a quick example. So let's say we wanted to have something on our site that predicted for the size of your house how much money you could get for your house. So that's something that looks at trying to find the correlation between how big a house is in square meters, meters squared, and what the cost is in pounds. And I think if you were to take a bunch of data, so let's say you've got 500 data points, let's call this m equals 500, so we've got 500 data points, m equals 500, then if we were to plot all of these on a graph, then we would probably be able to see with our naked eye, there's kind of a trend there. And if we were to be given a new data point, so x meters squared, we could probably say roughly where on the graph that would be, and come up with a hypothesis of what we think that house would cost. And the idea behind linear regression is that we come up with an algorithm that allows a machine to do that. And maybe at the moment we don't see why we would do that, since we can just plot it in Excel and see what the answer is. But this illustrates some of the concepts, which I'll reuse in other context a bit later on. So if we were to do this ourselves, we could probably come up with a line that best fits that data. And there's a way algebraically of describing this line. Does anyone know what that algebraic expression is? Y equals ax plus b, where a describes what the slope is, and b describes how far above or below the line it is. So if it was, if b was negative 500, then the line would start way down here, for example. So just with these two things, so multiply x by a and add this term here. Just by coming up with these, you can figure out, you can describe what a line is. And basically in linear algebra, linear regression, what we're trying to do is run an algorithm to guess what a and b are. So in machine learning, we tend not to use a and b. There's a convention that we use theta instead. So theta 0 times by x 0 plus theta 1 times x1, lowercase theta. Where we introduce a new term, theta x0 just for fun, and so that the maths all works out. This is equal to 1 usually. So we're trying to guess what these two are, and the way that linear regression works is that you first of all start with a guess. So you set theta 0 to be, let's say, 5, and you set theta 1 to be some other number 7. You just randomly select those, and then you see how well you did with those guesses. So what we're doing here is we're coming up with a function that describes our hypothesis. Our hypothesis is that this green dot sits here on the line. So if your house is 50 square meters, then it's worth, let's say, 300k. That's the hypothesis that we're trying to get a machine to come up with. So for a set of x's, where x's are the meters squared, so we've got some data that says 50 square meters is 300, 75 square meters is 450, and 100 square meters is, let's say, 600. This set of data here, we call this our training data. And if we've got 500 of these, then that's a good size to start training your algorithm to guess what good values are for theta and theta 0 and theta 1. Does that make sense so far? Mm-hmm. Yeah. So this is called our training set, and a lot of what makes machine learning work well is when you've got a good set of data to start with. So if we've got m of these, then that's all of these plots here. So what you do is you come up with a hypothesis function. So h theta of x, so this is h of x, which is parameterized by theta, and that's equal to theta 0 x 0 plus theta 1 times x1. Right, so that's our hypothesis. So we'll take these two values of theta, we'll times it by x, we'll add it to this times by x, and that's our version, that's our guess for what y is. So if you put 50 into here, then you'd expect this to pop out 300, wouldn't you? And depending on what you've set theta 0 and theta 1 to, it may or may not give up 300. So if we just guessed these to be 5 and 7, unlikely that when you put 50 in here that's going to give out 300. It's going to give you something else. So if this is our training set, then it's going to give us back something which is, let's say, h theta of x, and let's say that that's 10. So that's way out, isn't it? We were expecting 300. That's given us an error of 290. We call that our cost. Okay, so you can call it error or cost, but in machine learning we tend to call it cost. And for some reason the convention is we describe that as j theta. So this describes, as you change theta, what happens to the cost. Does the cost go up or down? And you can imagine that there's some curve where we've started, let's say here, on this curve, we're wrong, we're very wrong. And as we change theta, we're either going to go that way or we're going to go that way. Our guess is going to get closer to the truth or it's going to get further away from the truth. So we then apply the third thing, which is called gradient descent, which is a way of saying, okay, so we know that we're wrong. We've also got a feel for how wrong we are, 290. We've got a feel for which direction we're wrong in, whether we need to go up or down. So let's try, we can see that we need to go up a little bit, so let's try going up. So that's gonna then reduce our cost. So what we do is we change the values of theta by some amount, and then try again. And there's some magic here. Well, actually, there's some maths here. It's, where you take the derivative of j of theta that basically says what your slope is at the moment. So we don't know what the right answer is, but we know that we're wrong, and we know in what direction we're wrong. So we know what the slope is. And so we're going to change these values of theta to be something different. And in practice, what it will do is it will move on each iteration a little bit closer to the truth. And then after a while, it will stop changing. And if we get things wrong, then it'll start going back up the other way. But after a while, it will converge on some point where actually it doesn't change very much from iteration to iteration anymore. And so we can stop. And what that will do is give us two values of theta 0 and theta 1 that are correct. Correct. They give a decent hypothesis for our values of x. So if we know what the real values of theta 0 and theta 1 are, so this might be 0.1 and this might be 400, let's say. We don't know what they are. Let's say that they're those. Then we've parameterized a function that can then give reasonable hypotheses all the time, for a given, as good as this data set will support. So that's the basics of it. You start with your hypothesis function, which is, in this case, trying to fit a line to some data, theta x 0 plus theta 1 x1. You then come up with a cost function that describes how you work out how wrong you are and in what direction you're wrong. And then you run gradient descent to change theta to try and slide down this cost curve towards being right. So that's a very basic example, and you wouldn't do that with only these two bits of data. And in fact, if you wanted to add something else, let's say x wasn't just size of house. Let's say you had x0, which was x1, which was size of house, and you had x2, which was some other thing.
Geography, where you are.
Yeah. Okay. Yeah. So postcode, because that's quicker to write than geography. Then this graph would be a three-dimensional graph, wouldn't it? And your points would be a three-dimensional shape within that. And okay, we can still work with that because we can visualize things in 3 dimensions. But often in machine learning, you're not working with 1 or 2 dimensions. You're working with dozens or hundreds or tens of thousands. And we did an exercise on the course where we were working with something that was hundreds of thousands. and millions is not, millions of dimensions. So obviously that's impossible for us to visualize. But machines are much better than us at spotting patterns in data, and so that's where you would use linear regression. And we've got -3 minutes. I just wanted to introduce these principles because these principles are used for, as well as linear regression, they're also used for, let's say, logistic regression, which is where if you've got two parameters, I keep getting that wrong, x1 and x2, and you've got a bunch of data points over here, and you've got a different bunch of data points over there. So everything's characterized by x1 and x2 in this dimension. Put things into one set, and things over here are in a different set. So this is basically like saying, is somebody sick or not? The example that was used in the course was, based on the size of your tumour and the colour of your tumour, is it cancer or not? Everything over here is not cancer, everything over here is cancer, for example. That's using these same three things, a hypothesis function, a cost function, and a gradient descent to figure out whether something's in a particular class or not. Another thing which is super exciting, which is these three things just blown up with a bicycle pump, is that if you have a unit like this that takes some inputs and gives an output, in the way that this hypothesis function does, takes some input and gives an output, it's characterized by some parameters, then you can start to plug these things together to make a network where this is plugged, this is connected to all of the, that's connected to that, that's connected to that, and that's connected to that, and so on. You get the idea, everything's connected to everything else. Where these are layers of neurons. And this is really exciting because just using those same basic elements, we're able to create a brain-like structure. This blew my mind, right? Where this thing is not able only to learn what the parameters are, it's able to learn what the algorithm is. So with just 4 neurons like this, actually with just 2 neurons like this, plugging into an output neuron, you can create AND gates and OR gates. If you added on another network, another layer into your network, then you can create XOR gates and NAND gates. So you can see that if you add more of these and more layers, then it starts to be able to put together, work out its own very complex algorithms for how things work. So in this very simple example, we're just fitting a line. A more interesting example would be to fit some kind of polynomial curve. An even better example is, it's not just learning that it's this multiplied by this plus this multiplied by this, but it's learning what the additions and multiplications and divisions are. It's learning the algorithm itself. So that's called neural networks, and that's about week 6 of this course that I did. And what I want to get across is that this is just a crazy powerful area of maths and of computer science that I think it's well worth us exploring. And I haven't even gone past week 6 in this course yet, and in this description. And I haven't even touched on AI, which is where you've got learning agents, where you incentivize them to do things. And you give them a lot of data over a while, they give you an output. But we're going to, I don't know if you can see, already start to think about some of the applications for this at Wealth Wizards. But I can see quite a few. You can imagine that this thing here could learn, for example, what our advice should look like. For a given set of advice cases, then usually our advice outputs are in this sphere, and if they're not in that sphere, then they're anomalous, for example. So that's an introduction to machine learning. If this kind of thing floats your boat, and you don't mind the idea of taking a matrix which is like 1,000 in this direction and 1,000 in that direction, and multiplying it by another matrix, then get in touch. It's if you want to be involved in this capability that I'm setting up, then it will need some investment outside of work time to go and brush up on your statistics and your linear algebra and probably a bit of your calculus, and then to start on learning machine learning. But it's a super fun and very powerful and very interesting concept. Thanks for stopping by.